Hello guys, welcome to Physics Grad. This is day 5 of daily quantum mechanics, and in this video we are going to understand what we mean by dimension of a vector space. So in this video we will understand what we mean by dimension of a vector space, and we will go through some examples and finally end with an important theorem. Alright, so let us get started. So this is the definition of linear independence of a vector space, which we had discussed in our previous video. So this is just so that you can recall. So you can, if you want to recall, you can pause the video and just look at this slide. And once we know this, we are now ready to define what we mean by dimension of a vector space. So a vector space V has dimension equal to n if it can accommodate a maximum of n linearly independent vectors. So the definition is quite simple. All we need to do is understand it with some examples now. Okay. So if the vector space has dimension n, then we are going to denote it as vector space V with the superscript n to indicate the dimension, and in brackets we are going to write R if the vector space is defined in the real field, and we are going to write C if the vector space is defined in the complex field. So that is the definition, and it is not that hard to understand this definition, but we are going to consider some examples so that we understand it better. So the first example is going to be our arrows, which we are already familiar with, and we have also discussed about them in our previous videos as well. So first we consider arrows in a plane. Okay. So in my previous video on day 4, we had considered this example and proved that if you consider only vector 1 and 2, then they will be linearly independent. If we consider only 1 and 3, they will be linearly dependent. If we consider only 1 and 4, they will be linearly independent. But if we consider three vectors together, then they are linearly dependent. So what we had indirectly shown in this example is that the dimension of this vector space is in fact 2. Now the reason for that is the maximum number of vectors that are linearly independent in this vector space is just 2. Because if you consider this case where we have 3 vectors, now if you choose any 2 of these vectors, they are going to be linearly independent. But as soon as you add the third vector, we can always write the third vector in terms of the other 2 vectors by multiplying it with appropriate constants. And that is how we in fact said that these 3 vectors are linearly dependent. So therefore in this example, we can get linearly independent vectors only when we consider 2 vectors which are not parallel. And as soon as we add a third vector in the plane, they become linearly dependent. So 3 or more vectors are always going to be linearly dependent in this vector space. So the maximum number of linearly independent vectors that this vector space can accommodate is going to be just 2 vectors, which was the case in example 1 and 3 here. But here these 2 vectors are linearly dependent. But if you consider just one vector, it's a linearly independent vector, because then the equation would be just a1 times 1 equal to 0, and this is true only when a1 is equal to 0. So a single vector is linearly independent. So, but when we consider these 2 vectors, they become linearly dependent because we can express vector 3 as a multiple of vector 1. So the point what I am trying to say is that in this particular example, we have a vector space whose dimension is 2, and that means that we can choose a maximum of 2 linearly independent vectors, but we can also choose one single vector which is linearly independent. So The thing is that if we have an n-dimensional vector space, then if we choose some set of vectors, for example, if we have a 5-dimensional vector space and we choose three random vectors, then it is possible to choose these three vectors as being linearly independent. But in a 5-dimensional vector space, we cannot choose, let's say, 7 vectors which are linearly independent, because then it violates the definition of the dimension of a vector space, because the dimension of a vector space is nothing but the maximum number of linearly independent vectors that we can pick from that vector space. So from a 5-dimensional vector space, if we are able to pick a set of 7 vectors which are linearly independent, that means it is no longer a 5-dimensional vector space. It should have been a 7-dimensional vector space. So that is what I wanted to say here. So in this example, the dimension is 2 because the maximum number of linearly independent vectors that we can choose from this vector space is just 2. So now let us consider one more example. Okay, so let's just complete this example first. So therefore, arrows in a plane, we can choose a maximum of 2 linearly independent vectors. So therefore, the dimension of this vector space is going to be 2. Okay, so now I'm going to consider our other familiar example which we also discussed previously, which is that of a vector space consisting of 2 cross 2 matrices where all the entries are real. Okay, so now let us consider this example. So how do we find the dimension of this vector space? So to do that, I'm going to first choose these 4 vectors, okay, where only one of the entries is 1 and rest all are 0. And if you check, going by the procedure that we discussed in previous video, you will indeed see that these 4 vectors are linearly independent. Okay, so now we already have 4 linearly independent vectors which we have chosen from the vector space M. So this vector space must have minimum dimension of 4. Okay, it may have more than 4, we do not know yet, but if we can prove that it cannot have more than 4 linearly independent vectors, then it is same as saying that the dimension of this vector space is actually 4. Okay, so that is what I am going to prove now. I am going to prove that you cannot have more than 4 linearly independent vectors in this vector space. So let us do that. So let us consider any other vector v whose entries are a, b, c, d, where not all of them should be 0, because if all of them are 0, they will be the null vector. So I'm going to consider a non-null vector, any vector which belongs to the set M. Okay, and if we observe, this vector can be written as a linear combination of these vectors which we defined earlier, that is these vectors. And how do we write them like that? So we write this as a times vector 1, b times vector 2, c times vector 3, d times vector 4. So a times vector 1 would be nothing but a 0 0 0, b times vector 2 would be 0 b 0 0, and so on. And if we add the 4 vectors, this is the vector that we are going to get. Okay, so this means that if I bring all of these 4 vectors to the left hand side of the equation, we are going to get this equation. Okay, but if you compare this equation with the definition for linear independence, so let me go there. So this is the equation. We say that if there exists ai which are not equal to 0 such that this type of an equation is satisfied, then that these set of vectors are linearly dependent. So now if we go back to our example, which is over here, we see that this equation is exactly identical to equation 1 in the definition, and we see that these have non-zero coefficients such that they sum up to the null vector, and therefore these 5 vectors become linearly dependent vectors. So that means that vector space M can accommodate a maximum of only 4 linearly independent vectors, because if we choose any vector, any fifth vector, then we see that the set will become linearly dependent no matter what vector we choose. So therefore we cannot have 5 or more vectors which are linearly independent in this vector space. So the maximum number of linearly independent vectors are 4. So therefore the dimension of this vector space is 4. Now again note that the choice of these 4 linearly independent vectors is not unique. Even in the case of arrows, here we could have chosen these 2 vectors as linearly independent, or these 2 vectors as linearly independent, or these 2 vectors as linearly independent. But the fact is that we can only choose at a time maximum of 2 linearly independent vectors in the case of arrows, and in this case we can choose only 4 linearly independent vectors at a time. So this is one such example which is different from just 1 0 0 0 0 0 1 0 and so on. So another such example would be these 4 vectors. These 4 vectors also will be linearly independent, and I have worked out why it is so. You can just go through it because it is the same procedure that we discussed in our previous video. So the point I am trying to make is that the choice of these vectors are not unique. Okay, the only constraint is that we cannot choose more than 4 linearly independent vectors at a time from this vector space. Okay, alright, so now we go to an important theorem which is a consequence of the definition of dimension of a vector space, and the theorem is as follows. So any vector v in an n-dimensional vector space can be written as a linear combination of n linearly independent vectors, which I call 1, 2 up till n. Okay, it means that any other vector apart from these n linearly independent vectors, and since the dimension is n, there can be only maximum of n linearly independent vectors. I can write any other vector as a linear combination of these n linearly independent vectors, and such that not all of ai are zeros. Okay, so now next let us prove this very quickly. So we assume that first we assume that we cannot write v as a linear combination of these vectors. So that means that we cannot have this equation, that is v is not equal to a1 times 1, a2 times 2 and so on for any values of ai. Okay, so now what I do is I multiply both sides with alpha such that alpha is not equal to 0, because if alpha is equal to 0, both the sides will become 0, and then I bring this guy to the other side, and the equation becomes alpha times a1 times vector 1 up till alpha times an times vector n minus alpha times v is not equal to the null vector, because still we have said alpha is not equal to 0. So this equality will hold only when alpha is equal to 0. Okay, otherwise this equality is not true. So moving on, I am going to write this equation as writing alpha a1 as a1 dash and alpha a2 as a2 dash and so on up till alpha n as an dash, and a n plus 1 dash is going to be nothing but minus alpha. So basically just compare this equation with this equation. All I have done is renamed these guys, okay, as a1 dash, a2 dash, an dash up till a n plus 1 dash. And we see that since here the equation is valid only when alpha is equal to 0, it means that all of these guys are going to become 0. These guys, which means this equation is valid only when all of these ai dash become equal to 0. Okay, and again if we compare this with the equation for definition of linear independence, what this equation is implying is that the n vectors plus the vector v form a set of n plus 1 linearly independent vectors, because the only solution for this equation is when all of these coefficients go to 0. But then the dimension of the vector space that we were in was actually n, sorry, not n plus 1, it was actually, oh, here it means, so what this implies is that the dimension of the vector space must be n plus 1, because we are having n plus 1 linearly independent vectors, not n linearly independent vectors. So this means that we can choose a maximum of n plus 1 linearly independent vectors. But then this means that our assumption is wrong, because initially vector space that we had chosen had the dimension which was equal to only n, not n plus 1. So our assumption that we cannot write V as a linear combination of these n linearly independent vectors is wrong, which means that it can be written. Okay, so therefore a vector V in an n-dimensional vector space can indeed be written as a linear combination of n linearly independent vectors. So we have proved the theorem, and the theorem is also straightforward, and we have indirectly seen this in the examples as well, where we had written the general vector. So if we go back to the case of example of matrices, we had written a general vector V as a linear combination of the 4 linearly independent vectors, because in this case the dimension was 4, so it is possible to write this. Okay, so once again, if you go through the example, again that theorem will be more clear to you. So with that, I would like to end this video. So thank you for watching. See you on day 6. Take care.